So let's take a look at how the second law plays out in an ideal gas law problem. I've got a problem here that tells me about 2 moles of monatomic ideal gas. It's initially in state A. I'm told what that pressure is, I'm told what the volume is, I'm told what the temperature is. The gas is expanded isobarically to state B. I'm told its volume and temperature before being cooled isochorically to state C with a pressure of 50 kilopascals and a temperature of 225 Kelvin. The gas is then returned to state A isothermally. What's the change in entropy of the gas along each step and for the complete cycle? I'm told the pressure, volume, and temperature at each of these states. So the pressure at A is 150 kilopascals, the volume is 0.025 cubic meters, and the temperature is 225 Kelvin. At B, because the pressure at A and B are the same, still 150 kilopascals, it's now increased its volume to 0.075 cubic meters, and it's increased its temperature to 675 Kelvin. Cooling it isochorically means that the volume's the same between states B and C, so the volume at state C is still 0.075 cubic meters. I'm back to a temperature of 225 kelvins because again I'm going to now compress the gas isothermally to get back to state A, so it's got to be at the same temperature, and I'm told that the pressure at state C is 50 kilopascals. So I know pressure, volume, and temperature in all 3 of my states. If I want to calculate out the change in entropy along each process, I just need to use the equation that we derived, the entropy change using an ideal gas. So here's the equation that I've got. So NCV times the natural log of final temperature over initial temperature, in this case B over A, plus the number of moles times the universal gas constant times the natural log of final volume over initial volume, so here VB over VA. When I plug in my values, what I end up calculating out is that the entropy change along this first step in going from state A to state B ended up being 45.7 joules per Kelvin. And the thing that I should check with this, if we'd done the first law problem to calculate out what the energy transfers were in moving around this cycle, I would have a value for Q, the energy transferred into or out as heat along process A to B, and it will be positive, which is consistent with the fact that I've calculated a positive answer here. We can do the same thing along our second step, so in going from state B to state C. Again, I'm going to start with the same equation. The one thing I recognize, of course, is that this was an isochoric process, which means these volumes are the same, which tells me that this term's going to disappear. If your volume ratio is 1, the natural log of 1 is 0, so the second term disappears in our calculation here. And so I get that this is simply plug in my values for the first, so 2 times CV in this case, since it's a monatomic ideal gas, is 3/2 R, times the natural log of, I've got my final temperature, the temperature at C, over my initial temperature, the temperature at B, and I get negative 27.4 joules per Kelvin. Again, that's consistent with the fact that in my energy calculation, I got that Q was negative along this process from B to C. Along my third step, we're going from C to A. This was an isothermal process, which means that the temperatures are the same at A and at C. So again, I've got a temperature ratio of 1, which means I want the natural log of 1, which is 0. So now the first term disappears. And to calculate out the entropy change along my process from C to A, I just need nR times the natural log of these volumes. And so plug that in, and I get an entropy change equal to negative 18.3 joules per Kelvin. And so I should check and make sure that that minus sign is consistent with the minus sign that we got for the energy exchange as heat in going from C to A. So I've calculated the entropy change along each step. What about for the complete cycle? So the entropy change for the cycle is just the entropy change from A to B plus the entropy change from B to C plus the entropy change from C to A. Adding those together, what I end up getting, lo and behold, is 0. And so again, this begs the question, is our calculation for the entropy change of our system consistent with the second law of thermodynamics? If I get that the entropy change for my cycle is 0, then I must have a reversible process. So is this a reversible process? And the argument that we're going to make is yes, because in drawing out how we went from A to B to C back to A, where we can see every point, right, this line is really a line of states that we pass through in going from A to B. And this line is a line of states that we pass through in going from B to C. A line showing us all the states we pass through in going from C to A. And so for each of these states to be well defined, our ideal gas has to be in thermodynamic equilibrium. In plotting this out, our system is going through what's known as a quasi-static process. The quasi-static process tells us that we're proceeding slowly enough that we can effectively treat our system as in thermodynamic equilibrium even as it's changing from state A to state B. If I have a quasi-static process, that means that I can go back. So the quasi-static process that said I'm going to go from A to some really close process to A also means that I can undo that step and go backwards. So in plotting this out and saying we have a series of quasi-static processes, what that means is we can go backwards. We're assuming no energy loss as our gas goes around the cycle. This is a reversible process.